If you ask an astrophysicist what the Milky Way looked like before the Big Bang, you won't get a visual description. The question itself pushes past the boundaries of our current physical models. General relativity defines the Big Bang as the appearance of space itself. There was no pre-existing void for a galaxy to inhabit, and no temporal before to measure. To address this breakdown of space and time, Stephen Hawking proposed the no-boundary proposal. Hawking used the analogy of the North Pole. As you travel north, lines of longitude converge until the concept of north loses its meaning. Similarly, as we rewind the universe to its beginning, time and space cap off into a fuzzy quantum state. To find the origin of the Milky Way, we must look past stars and gas and search for a specific architectural seed buried within that fuzzy state. That seed is known as a quantum fluctuation. In the pre-cosmic era, energy fields were not perfectly smooth. They fluctuated with microscopic variations in density. These fluctuations existed at a subatomic scale, occupying a volume significantly smaller than a single atom. One of these microscopic ripples served as the initial seed, providing the density irregularities that would eventually guide the formation of the Milky Way. Moving that seed from the quantum realm to a macroscopic scale required a period called cosmic inflation, an epoch preceding the hot Big Bang. During this phase, space was dominated by a high-energy false vacuum. This energy caused space to expand exponentially, moving faster than the speed of light. This phase expanded the microscopic quantum ripples into massive topographical waves. As inflation ended, these waves became fixed as density variations in the geometry of the universe. We can isolate a single region where the density was slightly higher than the surrounding space. This region of higher density is the physical embryo of our galaxy, established in the moments before the Big Bang released the universe's matter and radiation. While inflation explains how the seed grew, the question remains, what state created the inflationary vacuum? The Big Bounce theory suggests a previous universe contracted until it reached Planck density. At this scale, quantum effects generate a repulsive force that drives a new period of expansion. An alternative model comes from Roger Penrose, who proposed conformal cyclic cosmology. Penrose suggests the infinitely expanded cold future of a previous universe mathematically loops back to become the hot Big Bang of the next. This implies the initial state of the Milky Way was an inheritance from a previous era of physics, a transition from an earlier cosmic state, rather than a spontaneous creation from nothing. As the timeline moves forward across the threshold of the Big Bang, the concentrated energy begins to convert into matter. Cold dark matter is drawn by gravity into the exact density peak left by inflation, creating a gravitational trap for ordinary matter. Hydrogen and helium gas then fall into this dark matter well, providing the material necessary to ignite the first stars. New evidence from the Gaia mission suggests the Milky Way's thick disk began forming stars just 800 million years after the Big Bang. Around 11 billion years ago, the Milky Way merged with dwarf galaxy Gaia Sausage Enceladus, adding massive amounts of gas and stars to the system. Over time, the turbulence of these mergers subsided, allowing the remaining gas to settle into the highly ordered thin disk where our solar system eventually formed. The sweeping band of stars seen tonight is the macroscopic result of that original subatomic ripple, a physical bridge between the modern galaxy and the quantum fluctuations of the pre-cosmic era.